We humans are curious creatures. Our innate curiosity drives us to explore, to question, and to seek out the unknown. From the moment we are born, we begin a lifelong journey of discovery, constantly learning and growing. This quest for knowledge is what sets us apart and propels us forward. We're driven by an insatiable thirst for knowledge, a relentless pursuit to understand the intricacies of our world. Whether it's through the pages of a book, the lens of a microscope, or the vast expanse of the internet, we are always seeking to expand our horizons. This desire to understand the world around us is deeply ingrained in our nature. We observe, we analyze, and we interpret, always striving to make sense of the complexities that surround us. From the smallest microorganisms to the vastness of the cosmos, our curiosity knows no bounds. And even what lies hidden beneath the surface, the Earth holds countless secrets, waiting to be uncovered by those with the determination and the tools to dig deeper. Archaeologists and geologists alike dedicate their lives to unearthing the mysteries buried in the ground, revealing the stories of our past. For centuries, our vision has been limited by what our eyes can perceive. The human eye, while remarkable, can only see so much. We have always been constrained by the visible spectrum, unable to peer beyond the surface of things. But what if we could see beyond the obvious? What if we could extend our vision, breaking through the barriers that have long confined us? Advances in technology are making this possible, allowing us to see the world in ways we never thought imaginable. What if we could peer through walls, delve into the earth, and uncover hidden structures? Ground-penetrating radar and thermal imaging are just a few of the tools that are enabling us to do just that. These technologies are opening up new realms of exploration, revealing what was once invisible, and unlock the secrets hidden from our view. Imagine being able to see the layers of the earth, to uncover ancient ruins without disturbing the ground, or to detect structural weaknesses in buildings before they become catastrophic. The possibilities are endless. This is the promise of penetrating imaging technologies. These tools are not just enhancing our vision, they are transforming it. They are giving us the ability to see beyond the surface, to explore the depths of our world in unprecedented detail. These remarkable tools are revolutionizing the way we see the world, allowing us to explore the unseen and unravel mysteries that have long captivated our imaginations. From uncovering ancient ruins to diagnosing life-threatening illnesses, penetrating imaging is transforming countless fields, allowing us to explore the unseen and unravel mysteries that have long captivated our imaginations. From uncovering ancient ruins to diagnosing life-threatening illnesses, penetrating imaging is transforming countless fields and opening up a universe of possibilities. From the medical field to archaeology, these technologies are making a profound impact. Doctors can now diagnose and treat conditions with greater accuracy, while archaeologists can explore historical sites without causing damage. The applications are vast and varied, each one pushing the boundaries of what we thought possible. Penetrating imaging is transforming countless fields and opening up a universe of possibilities. Engineers can inspect infrastructure for hidden flaws, ensuring safety and longevity. Scientists can study the internal structures of objects, leading to new discoveries and innovations, and opening up a universe of possibilities. The potential applications of these technologies are limited only by our imagination. As we continue to develop and refine these tools, we will undoubtedly uncover new ways to use them, further expanding our understanding of the world. The electromagnetic spectrum holds the key to this new era of discovery. By harnessing the power of different wavelengths, we can penetrate solid objects, revealing their internal structures and compositions. This ability to see beyond the surface is revolutionizing our approach to science and exploration. By harnessing the power of different wavelengths, we can penetrate solid objects, revealing their internal structures and compositions. This ability to see beyond the surface is revolutionizing our approach to science and exploration. We can penetrate solid objects, revealing their internal structures and compositions. This ability to see beyond the surface is revolutionizing our approach to science and exploration, revealing their internal structures and compositions. This ability to see beyond the surface is revolutionizing our approach to science and exploration. From medical diagnostics to industrial applications, the impact of these technologies is far-reaching. This essay will delve into the fascinating world of penetrating imaging, exploring the science behind these technologies and their profound impact on our lives. We will examine how these tools work, the principles that underpin them, and the incredible discoveries they have enabled. Exploring the science behind these technologies and their profound impact on our lives. We will examine how these tools work, the principles that underpin them, and the incredible discoveries they have enabled, and their profound impact on our lives. We will examine how these tools work, the principles that underpin them, and the incredible discoveries they have enabled. From the medical field to archaeology, these technologies are making a profound impact. Join me on this journey as we explore the frontiers of human perception and discover the incredible potential of seeing the unseen. Together, we will uncover the mysteries that lie hidden beneath the surface and unlock the secrets of our world, and discover the incredible potential of seeing the unseen. The journey of discovery is never-ending, and with each new advancement we come closer to understanding the world in all its complexity and wonder. Penetrating imaging technologies encompass a diverse array of tools. Each utilizes different principles to unveil the hidden world beyond our direct vision. Ground penetrating radar (GPR) employs radio waves to map subsurface features. Synthetic Aperture Radar (SR), mounted on satellites and aircraft, can penetrate clouds and foliage, providing valuable data for various applications. Wi-Fi imaging leverages the pervasive nature of Wi-Fi signals to see through walls, offering potential applications in security and disaster relief. Electromagnetic wave imaging, encompassing terahertz and millimeter wave technologies, enables high-resolution imaging for medical diagnostics and material analysis. Acoustic imaging utilizes sound waves to create images of objects and structures, playing a crucial role in fields like underwater exploration and medical imaging. Innovations in magnetic resonance imaging (MRI) are pushing the boundaries of medical diagnostics. They provide increasingly detailed views of the human body. These technologies, though diverse in their methodologies, share a common goal: to extend our perception beyond the limits of visible light and provide a window into the unseen. Ground-penetrating radar (GPR) is a geophysical method that has revolutionized our ability to explore the subsurface. This technology has opened up new possibilities in various fields, from archaeology to engineering, by providing a non-invasive means to investigate what lies beneath the ground. It utilizes electromagnetic waves, specifically radio waves, to detect and image buried objects and structures. These waves are capable of penetrating the ground and reflecting off different materials, allowing us to create detailed images of the subsurface. The principle behind GPR is relatively straightforward. It involves the transmission of radio waves into the ground and the subsequent analysis of the reflected signals. This process can reveal a wealth of information about the subsurface composition and the presence of various objects. An antenna emits short pulses of radio waves into the ground. These pulses travel through the soil, rock, and other materials, interacting with different subsurface features along the way. These waves travel through the subsurface until they encounter a change in material properties. This change could be due to variations in soil composition, the presence of buried objects, or other subsurface anomalies. This could be anything from a buried pipe to the boundary between different soil layers. The ability to detect such variations makes GPR an invaluable tool for a wide range of applications. This change in material causes some of the radio waves to be reflected back towards the surface. The reflected waves carry information about the subsurface features they encountered. A receiving antenna detects these reflected signals. The data collected by the receiving antenna is then processed to create images of the subsurface. The time delay between the emission of the pulse and the reception of the reflected signal provides information about the depth of the reflecting object. By analyzing these time delays, we can determine the depth and size of subsurface features. By systematically moving the GPR antenna across the ground, a two-dimensional profile of the subsurface can be created. This profile provides a cross-sectional view of the subsurface, revealing the location and depth of various features. These profiles can then be assembled to generate three-dimensional images, providing a comprehensive view of the hidden world beneath our feet. This 3D imaging capability is particularly useful for complex subsurface investigations. GPR has found widespread applications in various fields. Its versatility and non-destructive nature make it an ideal tool for many different types of investigations. Archaeologists use it to map out ancient ruins and burial sites without the need for destructive excavation. This allows them to preserve the integrity of the site while still gaining valuable insights into its history. Engineers rely on GPR to locate underground utilities, assess the integrity of roads and bridges, and identify potential hazards before construction projects. This helps ensure the safety and success of their projects by providing critical information about the subsurface conditions. Environmental scientists also use GPR to study soil contamination, groundwater levels, and other environmental factors. By providing detailed images of the subsurface, GPR helps them understand and address environmental issues more effectively. In forensic investigations, GPR can be used to locate buried evidence, such as weapons or human remains. This non-invasive method allows investigators to search large areas quickly and efficiently. The mining industry benefits from GPR by using it to detect mineral deposits and map out the geology of mining sites. This helps in planning and optimizing mining operations. In agriculture, GPR is used to assess soil health, monitor irrigation systems, and detect subsurface obstacles that could affect crop growth. This information helps farmers make informed decisions to improve their yields. Urban planners use GPR to map underground infrastructure, such as pipes and cables, to avoid damaging them during construction projects. This helps in the efficient planning and development of urban areas. The military uses GPR to detect landmines and unexploded ordnance, ensuring the safety of personnel and civilians in conflict zones. This application of GPR saves lives and prevents injuries. Even in space exploration, GPR plays a crucial role. It has been used on Mars rovers to detect subsurface ice and study the planet's geology. This helps scientists understand the history and potential habitability of Mars. As technology advances, the capabilities of GPR continue to expand. New innovations are making GPR more accurate, efficient, and versatile, opening up even more possibilities for its use in the future. Synthetic Aperture Radar, SR, takes penetrating imaging to new heights, literally. This advanced technology has revolutionized the way we observe and understand our planet. By leveraging the motion of radar platforms, SR can create highly detailed images that were previously impossible to obtain. Whether it's monitoring urban development, assessing natural disasters, or studying environmental changes, SAR provides invaluable insights that help us make informed decisions. Unlike traditional radar systems that rely on a single stationary antenna, SR utilizes the motion of the radar platform, which could be a satellite or an aircraft, to create a synthetic antenna that is much larger than the physical antenna. This synthetic antenna allows for a much higher resolution, enabling us to see finer details on the Earth's surface. The ability to generate such high-resolution images is crucial for a variety of applications, from military surveillance to environmental monitoring. This synthetic aperture allows SR to achieve significantly higher resolutions than conventional radar systems. The high-resolution images produced by SR can reveal intricate details of landscapes, urban areas, and even individual structures. This capability is particularly useful in urban planning, where detailed maps are essential for infrastructure development and disaster preparedness. Additionally, SAR's high resolution is invaluable for scientific research, providing data that can lead to new discoveries about our planet. It can penetrate clouds and foliage, making it an invaluable tool for remote sensing applications. Traditional optical imaging systems are often hindered by weather conditions and dense vegetation, but SR can see through these obstacles, providing clear images regardless of the environment. This capability is particularly important for monitoring tropical rainforests where cloud cover and dense foliage can obscure the view from optical satellites. With SR, we can monitor deforestation, track wildlife habitats, and study the effects of climate change in these critical regions. The basic principle of SAR involves emitting radar pulses towards the Earth's surface and measuring the time delay and strength of the reflected signals. These radar pulses travel through the atmosphere and bounce back from the Earth's surface, carrying valuable information about the terrain and objects they encounter. By analyzing these reflected signals, scientists can create detailed maps and models of the Earth's surface, revealing features that are invisible to the naked eye. As the platform moves, the radar illuminates the target area from different angles. This multi-angle illumination is key to SAR's ability to create detailed images. By capturing radar signals from various perspectives, SR can build a comprehensive picture of the target area, highlighting features that might be missed by a single-angle view. This technique is particularly useful for studying complex terrains, such as mountainous regions or urban landscapes, where different angles can reveal different aspects of the terrain. By processing the reflected signals from these various angles, SAR can construct detailed images of the Earth's surface. The processing involves sophisticated algorithms that combine the data from multiple radar pulses, enhancing the resolution and clarity of the final image. This process allows SAR to produce images that are not only highly detailed, but also accurate, providing reliable data for a wide range of applications. From mapping geological features to monitoring urban growth, SAR's detailed images are a powerful tool for understanding our world. SAR's ability to penetrate clouds and operate day and night makes it an essential tool for monitoring natural disasters. In the aftermath of a flood or earthquake, rapid assessment is crucial for effective response and recovery. SAR can provide real-time images of affected areas, even in adverse weather conditions or during nighttime, when optical satellites are ineffective. This capability allows emergency responders to quickly assess the extent of damage, plan rescue operations, and allocate resources where they are needed most. It can provide crucial information for flood mapping, earthquake damage assessment, and volcanic eruption monitoring. By analyzing SR images, scientists can track the progression of floods, identify areas at risk of further flooding, and monitor changes in the landscape caused by earthquakes. SAR can also detect subtle ground deformations that may indicate volcanic activity, providing early warning of potential eruptions. This information is vital for protecting lives and property, as well as for understanding the underlying processes that drive these natural disasters. In environmental monitoring, SR is used for deforestation mapping, glacier monitoring, and oil spill detection. The ability to see through clouds and foliage makes SAR an ideal tool for tracking changes in forest cover, assessing the health of glaciers, and detecting oil spills in the ocean. These applications are critical for managing natural resources, protecting the environment, and mitigating the impacts of human activities. By providing accurate and timely data, SAR helps policymakers and conservationists make informed decisions to preserve our planet's ecosystems. Its ability to penetrate foliage allows it to map the Earth's surface even in densely vegetated areas. This capability is particularly valuable for studying tropical rainforests where traditional optical imaging is often obstructed by thick vegetation. With SR, scientists can create detailed maps of forest structure, monitor changes in vegetation, and study the impacts of deforestation and land use changes. This information is essential for understanding the dynamics of these critical ecosystems and for developing strategies to protect them.